Welcome everybody. Today we're going to solve the equation of motion for a spring without friction. Now we could solve it for friction, but we're ignoring friction not because it's hard and we can't do it. We can do it because we know differential equations, but that's for another video. Today we'll look at this system of a mass and a spring with a spring constant of k and write the equation of motion and solve it. We will use Hooke's law, which tells us the relationship between the force that the spring applies on the mass and the distance from its equilibrium position. So Hooke's law tells us that force of the spring equals minus kx. This law tells us that if we pull this spring to this side, to this direction, the spring will apply force on this direction. And it makes sense. If we pull the spring like this, then the spring will go back to its initial position. It will want to go back into its initial position, but if there is no friction, it will pass the equilibrium position and then go back. Similarly, if we compress it like this, it will apply force on this way. So this is why the minus sign is here. And k is just a constant, and k is always positive. It has units newtons per meters, when it multiplies with meters, it gives us newtons. Talking about Newton. Newton's second law tells us that force equals mass times acceleration. And acceleration is the second time derivative of position. I will denote time derivatives with these little dots on x. So this is the second time derivative of position. So let's write it here. So x double dot is equal to d squared x over dt squared. So this is the second time derivative of position. If we substitute mx double dot into this equation, we get a differential equation. And it's a second order differential equation. Now this is the equation of motion for this spring without friction. To have the standard form of a second order differential equation, we will send minus kx to this side. So we will divide both equations by m and send this term to this side. So we will have x double dot plus k over mx equals 0. This is a second order differential equation, and to solve this equation we will use a method called Ansatz. Ansatz means guess in German, and that's what we're going to do. We're going to guess a solution and then substitute that solution into the equation to get a general form. Now we will guess that this differential equation has a solution in the form of e to the rt. We don't know what r is, and this is what we're going to try to find while substituting this into the equation. When we differentiate e to the rt twice, we get r squared e to the rt. We can factor out e to the rt in this equation. And now we have two terms, e to the rt times r squared plus 1. Now, for this whole equation to be 0, either e to the rt or r squared plus 1 must equal 0. And e to the rt can't be 0. It's an exponential term and it can't be 0. So we can just divide both sides by e to the rt to cancel it out. And we are left with r squared plus 1 equals 0. I made a little mistake that 1 should have been k over m. So now just see the equation as r squared plus k over m equals 0. And this equation is the characteristic equation of this differential equation. And it's really important. So if you knew this method, you would just look at this equation and write this equation, because you have two derivatives here. It's r squared, and you have no derivative, so it's just k over m. It's like the ax squared plus bx plus c, the quadratic equation. It's just like a quadratic equation, and this is the characteristic equation of this differential equation, and it will help us to find the general solution to the differential equation. To solve this quadratic equation, we send the k over m to the other side, and we see that r squared equals minus k over m. And m is positive. It's the mass of this block. It's that object. It can't be negative. And in the beginning of the video, I said k is a positive constant, so it can't be negative. So this means that this number as a whole is a negative number. And it's equal to the square of the r. which means r is a complex number. So r equals plus or minus I square root of k over m. Now I'll just ignore the minus part and just focus on the plus, the positive solution. I root k over m. This root k over m has a significance. It tells us something physically. And we will name this as omega. Omega is the angular frequency of this object, and it's equal to the root of k over m. And it's important, it will come out later, so we'll just name it as omega instead of writing square root of k over m all the time. So the r is equal to I omega, and we said x of t, so the solution to this differential equation, was e to the rt. So we will substitute r, I omega, and we'll get the equation x of t equals e to the I omega t. Now, we don't like this, because it's a complex number, and the differential equation we had didn't have any complex components, and it's representing something real, something physical. How can the equation of motion of this spring, of an object in a spring, can be a complex number? It doesn't make sense. So we need to take out the real part in this complex number, and by doing so, we will utilize Euler's formula. Now, Euler's formula tells us that e to the I theta equals cosine theta plus I sine theta. And we have e to the I omega t. We will use Euler's formula and plug in omega t as theta to get cosine of omega t plus I sine of omega t. Now, this is the solution we find. And this is not the general solution. It has no any constants in it. We need to have two constants because it's a second order differential equation. Now, we will use a theorem in differential equations that helps us solve differential equations involving complex numbers. So if u plus iv, so u and v are not numbers, they are functions, is a solution, then u and v are solutions. So we have cosine omega t plus I sine omega t. These are two different functions. One of them is multiplied by a complex number, one of them is a complex component of this. And if this whole thing is a solution, each of these parts, cosine omega t and sine omega t, are separate solutions. It's an easy theorem to prove, so I won't prove it, but we'll just take it as granted to solve the problem. So cosine omega t and sine omega t are solutions. Now we have two solutions for the differential equation. They are not general solutions, they're just particular solutions. Cosine of omega t and sine of omega t. And in a differential equation, in differential equations, if we have two linearly independent solutions for a second order differential equation, then any linear combination of those two equations is a solution. What does this mean? This means if these two equations are linearly independent means if you can get this equation, get x2, by multiplying x1 with a number, then they are linearly dependent. So if c, which is just a real number, c times x1 equals x2, then they are linearly dependent. x2 is a scalar multiple of x1. In this case, sine omega t is not a scalar multiple of cosine omega t. We can't just multiply cosine by 5, 10, 20 and get sine omega t. They are linearly independent. So any linear combination of cosine omega t and sine omega t is a solution to the differential equation. And by a linear combination, I mean just multiplying the first one with a number and multiplying the second one with a number, then adding them up. So yes, this is the linear combination of cosine omega t and sine omega t in its general form. C1 times cosine t and C2 times cosine sine of omega t. So C1 and C2 are just numbers, they're just constants, and they depend on the initial conditions of the differential equation. So it might give us some initial conditions saying that the initial position is 0, initial velocity is 0, and we need two boundary points, two initial conditions, because this is a second order differential equation. And without giving any initial conditions, without specifying any boundaries, this is a general solution for the differential equation. Now, we solved the second order differential equation, which we constructed using Newton's second law, and found out that x of t, the position of this spring as a function of time, is equal to c1 cosine theta plus c2 sine theta, where c1 and c2 are just real numbers. And we knew the initial equation, this force equals minus kx. It was the function, the force as a function of position, and it was too easy. Force just depends on the position where you're at. But we didn't know position as a function of time. That was the hard thing, and now we did it. Now let's interpret this solution. What does it mean? If we start at some point, if we just pull it in time, which is t is a variable, it will just oscillate forward and backward when we pull it in time. So the force just depends on position. So if we pull it so far, then it will pull it so strongly with a greater force. And how does the position change? These two trigonometric functions explain that. Position just oscillates back and forth. And because we ignored friction, there is no decaying term. This oscillation doesn't get slower and slower, and it doesn't stop at some point. Because we ignore friction, it just goes on indefinitely. It just oscillates back and forth, and it never stops. This omega, which is equal to square root of k over m, this is the angular velocity of this. But this is in front of the time in the cosine and sine, which is why it's the angular frequency of this spring. It's the velocity as it goes back and forth. So if we had friction, which we will have in the next video, this spring slows down and stops at some point. In this case, because there is no friction, there is nothing to stop it. It just goes back and forth, oscillates without stopping. And this is what this differential equation tells us, and this solution tells us. Thanks for watching.